Linked it and everything, I shared it. So,
Yeah, but it's on the GitHub.
I haven't
Sorry,
seen that
okay.
yet.
Sorry, you guys muted. Can you mute
I
yourself?
mean, the point I went on is, quit making those ships somehow.
Right.
Somebody.
Sorry, can you mute yourself? Okay. All right, so 9:05. I think I'll go started. So, okay, the people still coming in. All right. Okay, let's get started. Welcome everyone. Good morning, good evening, good afternoon, and I know there's a different time zones. So my name is Chester Chen. I'm part of the NVIDIA FLARE teams. So today's is a NVIDIA FLARE webinar, like a Q3 webinar, and it was organized by the AI Camp, San Francisco Big Analytics. San Francisco AI, I think the name have changed, but it's basically part of the AI Camp.
NVIDIA agents.
Sorry, I have to mute you. I have to mute you all. Sorry. So as part of this, so we have this quarterly events and online events, basically talk about the federal learning and federal learning related framework and the NVIDIA FLARE, and we'll showcase our latest development. So today's, we pretty much break out into 3 sessions. So the first part is I'm going to give an overview especially for folks who haven't really worked with FLARE, and introduce give an overview of what NVIDIA FLARE is about, and our use cases and our key product features in very high level. And then after that, I'll be diving into our latest development in upcoming release 2.9, and which will talk about the FLARE working with agent, agent skills. So I do a little demo, and then I will pass on to my colleague Holger, who's talking about the other part of the auto research using agent skills, and then I will pass to Peter, who's the talk about how do we NVIDIA FLARE to scales any type of runtimes. So so that's kind of the agenda. Without further ado, and I'm going to share my slides. Give me a second. So let me see. Can you see my screen?
Yes.
Okay. Okay, cool. So I know people still keep coming. So just very quickly for people who doesn't really have worked with federal learning or NVIDIA FLARE, this is kind of a quick, quick intro. Say what is a federal learning? So federal learning is kind of this idea of kind of a distributed computing, in a sense, a distributed learning, and where in this particular cases is the data stays local, the intelligence moves. So for example, in this case, we want to work together with the other collaboration. So it's a federal learning kind of is a first part is a decentralized. The second is privacy preserving. The part is emphasizing is a multi-party collaborate together. So it's kind of a training with preserving AI with the multiple parties, building a model together. So without moving data. So if you look at the picture on the right, so suppose I want to train a model together with 2 hospitals. So instead of us put all the data into one central data lake and then train there, in these cases, you keep the local hospital data stay in local, but instead you're sending a model to the hospitals. So suppose you have a global model, so essentially just randomized initialized model or pre-trained checkpoints, and you send it over to 2 hospitals, and then you train them locally at each hospital, but then you ensure the model weight with this kind of a central aggregator. And then you re-aggregate the model and send it over again, kind of a loop this over again, until either the convergence or you decided to stop at a certain number of rounds. So that's kind of the core ideas. Of course, there's a different nuances, all kind of variations. By doing this, essentially one part, you're basically saying, since your data never moves, this kind of reduce the data privacy leaks because the data never leave your hospitals. The second part is the attack surface is reduced because before you have this whole data people can attack, but now you can only attack, the model weight, all the other stuff. The third part is there's a lot of regulations from Europe, Asia, U.S. altogether. Depends on whether it's a gRPC or Europe AIX, all the other stuff. Many of them basically say, well, the data you cannot leave the country or leave the region. So that's kind of by this kind of a technique can help to compliance with a regular compliance. And the last one, so some cases, even though these, privacy or regulation is not the main driver. So basically, it's my own data and I can move. But sometimes economically, it's hard to move the data because the data volume is huge. So there's multiple reasons for doing this type of federal learning. So next thing is, what is NVIDIA FLARE then? NVIDIA FLARE stands for, FLARE stands for Federal Learning Application Runtime Environment. So it's kind of open source, Apache 2 open source SDK basically help to, facilitating this kind of a collaborations. It's kind of a framework for you to do this. So it's totally free, use any way you want it. And so in the software itself was built during COVID, essentially, Holger and others tried to train a model to predict the oxygen tank usage, so which patient you gave to this oxygen tank during COVID. So they basically, the 20 hospitals work together around the globe. And essentially, that's where the early stage of the FLARE, and over time, we built this from, enterprise. So basically from get-go, this is, needed to be ready for production. So FLARE is basically enterprise skills and production ready. It's very mature. We've been using this for many hospitals, and I'll show you in a second. And very secure and scalable. We're conscious about the privacy and compliance. So there's additional techniques into how do you protect the model weight being attacked. So there's techniques such as differential privacies, homomorphic encryptions, confidential computing, and I'll talk more on those. FLARE is model agnostic. So in other words, you can train any kind of a model. So we don't care is a traditional machine learning model or deep learning models, whether it's biology or whether it's a fraud detection. So we really don't care what the model is and whether it's TensorFlow, and we support all that. And we'll have a very simple API. So literally you can change any existing training code within 10 lines of code. It will become a FLARE's federal learning code. So of course, in order to do this, and we not always have a setup big machines and around multiple machines, but you can simulate this from your local machines, and we build the simulators, and also simulating the deployment, and then also of course we can deploy it in the large scales productions. So whether it's on-premise, on cloud, and hybrid environments, we support them all. So I'll touch more on some of these cases later, but first part I say, okay, great. So I know what FLARE is and what federal learning is, who using them. So FLARE has been used quite, extensively around the different use cases, particularly in healthcare, life science, and financial services. So these are, in healthcare and mostly, a lot of use cases in cancer research. So, as we talk, and this is the slides that were built, maybe 6 months or 7 months ago. And I haven't really updated it, but at that time, so we have at least a half dozen of the active projects, around the globe. So many 60 plus and even 100 plus institutions, basically including many major cancer centers, training all kind of cancer models. The other big category is the drug discoveries. Essentially, that means that multiple drug companies are working as a consortiums, and they basically try to come up new folding models or new kind of properties of the chemical properties through these collaborations. So there's also rare case of diseases and clinical trials and many other use cases. Financial services are mostly focused on the fraud detection, anti-money laundering, and there's other cases like a mule account detection. So those are kind of the financial areas, and usually several banks work together. The other categories, and I would just bluntly call them scientific computings or national securities. And so most are, like, for example, national labs and any other labs work together, for scientific purpose and all other large language model trainings. Transportation is another area. So basically, there's a cross, either basically using for self-driving cars or either as data centers for self-driving car data, or basically in-car, model predictions through a different device, like for example, different trucks or different cars, and then give you different, kind of different collaborations. So I'll just show you a few examples that's being in productions, people using. One of the use cases is Eli Lilly. Eli Lilly, they have building machine learning models for drug discovery for a while. So they decided to start something new a year ago, and then they built a new company, new subsidiary called TuneLab. This TuneLab basically decided to essentially give away, I think at the beginning it was 13 or 16 models, which is based on their publications, that is worth about $1 billion using their train them data. So these gave them for free for the other startup to use. So the other startups can use this for free, but in exchange, they can help you to fine tune these models. So it's kind of a win-win situation. TuneLab can basically, get the model tuned and, see what's the latest uses from the other startups. The startup, wet lab and all the others can start from, not from scratch, but also from, better models as a starting point. So that's kind of a win-win situation. So this program, as far as I know, has been a great success. And actually, Eli Lilly going to have 1 year celebrations in September, early September, in San Francisco. So the number of startup participation has increased dramatically. So the second case is called a Cancer AI Alliance, and this is also over a year now. So they actually announced the initial start at last year's FLARE Day and the announcement. So this kind of a 4 medical centers, top tier medical center in the U.S. get together, that involves the Dana-Farber, Frank Hutch, Johns Hopkins, and also the Memorial Sloan Kettering Cancer Center. So they supported by all the cloud, Amazon, Google, Microsoft, and also have AI2 and the data, support from Solidum, and of course NVIDIA and Deloitte help to managing. So this kind of a lot of technology partners as well as the major medical center work together. So they want to try to build is essentially a research platforms for the cancer researchers to be able to quickly solving their cancer research, not in years, but in months or even shorter. So before that, in order to get some data to do the research, it takes a lot of approvals and go through the right data, probably several years to get something approved. But now they want to be able to parallelly, do a lot of research together. So the initial pilot is 8 projects. So they've been have a great success, and they are actually giving a talk in this year's NVIDIA FLARE Day in September. So the other cases is a recent study by the several banks, particularly JP Morgan Bank New York, a Royal Bank of Canada, plus Deep Temple is a fraud detection startup. And together with the NVIDIA FLARE, Hoger is one of the main drivers of this research with these banks. So you see the papers on the right-hand side. The picture is actually the all the some of the representatives from the 3 banks talking at the last year GTC in Washington D.C. So different category again here in this case is national security. Essentially, national security also try to leveraging these latest AI development and try to train a large language models with the classified classified materials and classified informations. But they like to collaborating with the other national banks. So in this case, for example, the Tri-Labs is the Sandia National Lab, Los Alamos, plus the Lawrence Livermore. So they try together, but of course they cannot share their information together directly. So they decided to using federal learning to train these models, as part of the this program. they're essentially, in this case, is they set up, remember there's all national labs, they cannot have a central server somewhere on the public cloud. So they have to almost like air gap them together. So in this particular case, the Sandia lab put the server, essentially the aggregator node, in so one of the Sandia lab, but everybody else has the other. So and then they're using swarm learning, use NVFLARE in these cases, and essentially do aggregation at the random selected nodes. And so they name this model they trained called a Chandler because that's a city kind of in the middle of all three labs. So they're continuing to train, and they're aimed to train like over 70 billion primary models. So next one is a kind of a think about a sovereign AI, kind of a government case. Essentially, this is the Taiwan government, the Ministry of Health and Welfare. Essentially, they try to make sure that in all their Taiwan data is using stay in Taiwan, and also all the wherever they produce the AI models can be validated through the other other hospitals, because in order to do a equivalent in the US like a FDA approval, they have an equivalent called TFDA, Taiwan FDA. So they need to make sure that these models are in order to get approved, is essentially validated. So to do that, they built a platform using FLARE to essentially building this kind of a external validation, clinical validation platform, organized by the Taiwan government. And initially there was 16 hospitals, and there's also 2 other foreign hospitals, like for example, Thailand and Sweden, willing to participate. So and that's the picture. Is our VP was as part of the inaugural launch in last January. Okay, so next one is a self-driving car case, but it's in NVIDIA's internal use cases. And so essentially, NVIDIA's try to train these models across the globe, and some using data from China, using US. But as we talked about it earlier, the regulation constraint in China data cannot move to US centralized training. So essentially, the self-driving car teams decided to build a cross-country federal learning framework, using FLARE to train these models. And so we established a data center in US and 1 data center in China, and then the coordinators actually in Japan. In that case, they're using this kind of they call cyclic or round robin type of training approach. And so they have been using this model for, this is an account notes right now, so 3 years now in production. So there's about a dozen of different models for example, the ones, the active models, for example, detecting vehicles, pedestrian, bicycles, monitoring, vehicle status, identify traffic lights, predict obstacles, and all kind of object detection type of things. So all kind of models. They have published multiple versions through this platform. So there's a lot more. I'm just giving you a sense of what this, what the kind of use cases are. So the next part, I'm gonna just quickly go through some of the FLARE features, and you see, what a FLARE looks like. So the first one is I talk about is, hey, you got 10 lines of code, and you can get a FLARE production. So how? So this is kind of one piece of the feature is that we call a client API. If you see the left side, this is like a CFARTN, classifier, type of a model. You have this very simple model. You get this, few lines of a standard PyTorch training or PyTorch, and then you're basically saying, okay, I have this training models already. I know how to train this in PyTorch. How to turn that into FLARE or federal learning training? So on the right-hand side, you see this is our client API to turn that into client-side training code. You see the highlighted pieces. Essentially, that's a 1, 2, 3, 5 different lines, including the import. Essentially, we don't change. You don't need to change your class, your restructure. You don't need to do any of those. So you're literally just add these 4 or 5 lines code. So we basically, import call it FLARE, and we init, and then we. In this case, sorry, this is not a PyTorch. This is a PyTorch Lightning. So in the case we call something called a patch. You patch the trainer. The trainer, essentially, we set up some callbacks behind the scenes, and then we, there's a while loop. So basically, allow you to detect whether it's still training, because as you remember, there's a round and round back and forth. So we detect what is the training. And then the callback we essentially will do is essentially receive the model from the server, and then update the local model, and then you basically do the local training, do a validation, and then do the fit, and then back and forth. When you're done, you send the model back. It's very simple. So essentially that, as I said, like a 5 lines of code you're changing to that model. So, and then you say, well, that's the client side training. How do I know I'm using weighted averaging? I'm using some other algorithms that, that federal learning has. So we have something called a recipe. So the recipe essentially will tell you, do you using cyclic, using fed averaging, or using any other machine learning, swarm learning, and any other things. And so have these, recipe made it ready. So on the left side, if you see, this is a fed averaging recipe. Essentially, it's just a one line changes. Of course, I break it up in multiple lines to make it easier to see. You get this fed averaging recipe, the December minimum number of clients, and how many number of rounds, and what's the initial model. And then the transcript is equal to client.py. Client.py is literally the last slides I show you, the 4 or 5 lines changes. You plug it here. In this case, you're using a simulation environment, so you can run it, and that's it. So if you want to say, oh, I want to use it in production, you literally change that simulation environment in production environments. And so it's a very simple lines of code. So that's kind of a API. So that's already simple. But some people say, well, the recipe means that you have something fed average, something you already built it. So what if I want to build my own? I'm a researcher. I want to build my own. So we got this another new, very simple API allow you to get a full controls. You can, by the way, you can still writing the existing ones, but this one, the without this, but this one makes this super, super simple. So this is our 2.9 release, which is, as I said, is in coming days, coming weeks. So this one is, you can see that if you want to decide to write your own algorithms, literally you write these few Python functions yourself, and then you just put an annotation on it. Like, for example, the one that we talked about training earlier. So we say here, suppose I define a training method called train on the client side. I annotated this, collab publish. That means that expose this train to the server in a sense. And on the server side is I get an entry point I call the collab main. And here I'm just saying fed average. I write my local average as abnormal. Except in one piece, I'm going to add a line, say collab client.train. So this one basically say, well, you're calling all the clients and the train method. There's a train equivalent, essentially matching this train. If you change this to train 2, here's a train 2. So essentially matching that method. And then you do a recipe, we have a collab recipe, and then you can just do execute. So essentially, what it does is essentially almost like you do this RPC call, essentially. And you can change any way you want it in this case. It's super, super simple. So this gave the research a lot of flexibility to experiments, all kind of algorithms, and it's very fast. So, okay. So we talk about the different APIs, but we're talking about now we say, hey, we're talking about an agent age, and how is a FLARE ready for the agent? So the first part we make the FLARE agent ready is basically build a really rich machine readable, machine ready, essentially agent ready CLIs. So command lines. And so because we believe that the agent interact with a FLARE is not reading bunch of Python code, it's mostly reading the command lines. So basically CLI is important. So basically modernize this with all the pretty much complete the system from deploy, from architecture, from the job executions, the system management, all are not only human easy, but also machine easy. So this is really agent ready right now. So you can. So I talk about the framework part. The framework models, I mentioned that framework ready. So we are literally just, you can support all kind of things. What is a medical imaging, what is biology, what is standard statistics, and graph neural nets, and all the other different models and XGBoost. So we support them all, and also we support different type of workflows. Fed averaging like a broadcast and getter type of patterns one. We talk about the swarm learning. Basically, you go to different clients and randomly select anyone and as averaging nodes. So you can do that. You can do cyclic. You can do split learning. In other words, you can take a deep learning, split the different layers in different clients or client and server. And then also supports the horizontal and vertical. The horizontal federal learning is kind of cases and all the clients have the same features, and the vertical is the ones they don't have the same features. And in terms of monitoring the progress of whether you see the loss and accuracy is going up and down, so you can using MLflow with some biases and a TensorBoard. All these will give you option to stream the losses or accuracies to the server, then talk to MLflow. So you don't need to worry about it yourself. You can see the whole complete picture from different sites. Of course, it's not just training. So FLARE has using for validations, evaluations. You can just give a model across different sites. And we'll also do this cross-site validation, basically compare one site with the rest of the other sites. So we talk about all the training, the evaluation, but FLARE itself is a building from as a federated computer rather than just a federated learning. Learning is just one applications. So we are being using for data discoveries, data harmonizations. So for example, different sites need to do data engineering together, essentially coordinated in ETL. Quality control, so essentially, do like out of distributions, data filtering, processing, analytics, and then there's a federated analytics, and also other global analytics, and also objective workflows, and we'll talk more in the future. So, as I said, FLARE is very emphasizing on the security, security and privacy. So basically, we build a lot of the security into this, including having private policies around the different sites, the site-specific policies, authentications, through their own organizations, adding the input filters and the result filters. You can apply these privacy filters on each site. And most recently, we also adding study. So we introduce a study. So in one platform, you can parallel has multiple studies, and then these data sets are isolated from each other through a study scope. So Peter will talk more on this. Okay, the other part of this privacy enhancing technology, this is the technology say, well, we talk about that we don't move the data, we move the model. What if people attack the model? So essentially try to do a model inversion attack and see whether we can extract the memberships or privacy informations out of these weights. So there's one technique from Google called the differential privacy. It's essentially adding noises kind of to the model itself. You can, when you're sending out, you can put a noise there, and or you do during the training. So it depends on how you apply them. FLARE support them. Homomorphic encryptions is another technique. So basically means that you can operate the mathematical operations in the encrypted space, and by the end you decrypt, and the final results are the same. So, so that's another technique. Of course, they all has this pros and cons. The confidential computing is another technique. Essentially, confidential computing is a hardware-based root of trust. In other words, the encryption keys and all the others are built in the chips. For example, AMD CPUs, Intel CPUs, and plus NVIDIA's GPUs, and that become the root of trust. And then they build on top of that, you have a multi-GPUs and also the kernels of the software, and then build on each layer. So by building that through this technique called attestation, so that you can lock down, put addition production using this so-called trust execution environment. I think I have one slide on that. Yeah, so this kind of I mentioned earlier. So essentially, you building a trust. So one way to leveraging confidential computing is we call the building explicit trust. So when two hospitals collaborating together, so once you had a connections, you say, I'm trust the other IT guy, but with confidential computing, you don't necessarily implicit trust. You can do explicit trust. Essentially, you say, well, let me make sure that your machine is not tampered. So how do we do that? Is there's something called attestation, which is giving a attestation token or report So you can exchange that to, you can independently verify that machine is trustworthy. By doing that, you're building explicit trust. The other part is, I mentioned that earlier. So what if somebody to attack the model weight? So suppose you're not using, differential privacy or homomorphic encryption. Of course, you can use that in combination, but suppose you're not doing that. You can use confidential computing to secure the server. And so in that case, nobody can log into that machines. So they cannot SSH to it, and they cannot, do a normal login to it. So there's nobody can access to the individual model weight. So in that way, you can secure the aggregation part. This is kind of a secure aggregation. The confidential computing can also secure the client side. So for example, if you building this is so-called a trust execution environment using confidential computing from the client side, suppose the client side is locked down. So the person who owned the machine couldn't log in to get into that trust execution environment. So this get important features. Essentially, you can do model IP protection. So for example, if I'm doing a training, I'm not really like to sharing my, send the model to you, but I don't want the model being copied away. Essentially, I want to preserve my model IP. So in that case, using confidential computing, the other part, you cannot access to it, essentially achieve the model IP protections. FLARE has built this MVP version last November, and then we continue to extend our support on this this year. So our next release, 2.9.1, will basically extend our existing on-prem support from both AMD CPUs, NVIDIA GPUs, plus the Intel TDX machines. We're actively working on that, and also our next release, 2.9.1, which is targeted to around October, mid-October, that will also support the confidential containers, which means that the VMs is in the Kubernetes clusters, so with the GPUs. So we're having more release on those pieces. So the last part is related to, where we can deploy it. So we can deploy it, as I said, it's pretty much anywhere. We can run edge, on-prem, on cloud. So to support highly scalable, not just a few hundred or nodes with, a few thousands of the devices, we also support, FLARE has something called hierarchical deployment. Essentially, you have multiple relay nodes. You can see the picture there. And then we have a web gateway in between, and then a lot of mobile devices can connect to. And we actually had both iPhone and Android, develop examples there, and you can connect to. So, but a majority of the cross-silo supports are basically on bare metals, Dockers, Kubernetes, and HPCs like high-performance computers, particularly on the Slurm side. So those are, Peter will dive more on that, and we can run pretty much on any cloud. Okay, so that kind of gave you what a FLARE is. And next one, I'm going to talk about, okay, what about the agent? So, FLARE has been, there's a two sides of stories. So if you think about an agent talking to FLARE, so basically FLARE is just another tool for agents. There's also agentic systems, which we will not discuss today, but we are discussing the first part, the FLARE as agent tools. In that cases, in order to agent be able to behave correctly or efficiently, so we need to developing agent skills. There are two categories of skills we develop. The first category we call conversion. The second part is for auto FL or auto research, which Holger will talk to. I'm going to talk. The first part is the conversion. That means that suppose I have a PyTorch I gave you earlier, even though it's a 4 or 5 line of code and another 4 or 5 lines code, 10 lines of code to get to. But suppose I'm a newbie, I just don't want to learn all these APIs and all that stuff, and I just just hoping an agent can do that for me. So if I gave you a PyTorch versions, convert that into whatever the API, FLARE recommended, just do that for me. So that's one type of problems. And that could be PyTorch, could be PyTorch Lightning, could be Hugging Face trainers. Just can you do that for me? Convert it automatically. So the second part is to say, okay, before I do the training, I need to do a statistics. So federated statistics, I get a one CSV, I get a one image files. Can you do a federated statistic job for me so I can just run it? So that's kind of a two type of problem. So we talk about how do we convert that? So instead of just talking to that, what I'm going to do is I'll do the do a demo first. So in this, because the agent take a few minutes, and so instead of watching it and waiting for a few minutes, and I come back to the slides after that. So I'm going to do the demo first. So I'm going to using, if you see this, this, I don't know, this is too smaller. Is it big enough? So I'm going to using codecs for as. So notice here, so I'm in this example called PyTorch conversion. So maybe I should first to see what the code looks like. So so here I have examples. On example, hello world agent skills. I have built a bunch of examples here. One is a FastStat image, Hugging Face conversion, Lightning conversion, PyTorch conversions. So what I'm going to do is, and there's a source code here and has a data. So I have pre-built some, very tiny data because I don't want this too long. So basically, and then I have this very simple models, like, small CNN models, very, very, very compact character level CNN models. So it's very simple models. Had some requirements and just need a torch. And I have this little training code. Let me try to find this. So yeah, so this is the main code, and just pass the arguments, and then set a seeds, and you load, made some training loader for the different data sets, right? And you put some arguments and say, vocabulary size, embedding dimensions, blah blah blah, and using this model, and then you make it, some labels. This is the standard stuff, and then you're sorry. So you do some training, and so this is kind of nothing to do with the fed learning, just a standard torch training. So this is the code I gave you, and I have a README here. The README basically show this is the structure, and you need to install something, and then you explain the data, and say, okay, in order to run, I literally gave a prompt. Say, the prompt is say, I have an existing PyTorch training projects in this directory. Convert this into fed learning using fed average. Validate it locally with the 2 clients, 2 rounds of training. So you may download any required public artifact, tokenizer or whatever. So if it is not cached, proceed without it. So this extra lines is kind of a building the, when we're building the skills, and there's the securities, and don't let agent to arbitrarily download anything on the internet unless you give them permissions. And so that's kind of a you need a time. Go ahead, you can download. So essentially that's what it is. So what I'm going to do is I'm going to cut paste this prompt and go back to my agent and let it run, and then we'll go back to. So this is the directory, right? So this is the PyTorch conversion directory. I'm going to just paste it here. See, oh shoot. And let's see. Paste. Nope, that didn't copy right. Let's go back here. Maybe I should use this. Let's see. Okay, I think I got it right. So this is the prompt. I'm just hit a return and see what happens, and then we'll go back to the slides when he's doing his work. So he says, I'm inspecting the projects, blah blah blah, and I'll make a smallest requirement, conversions, and then start doing his, start doing his thing. So this is an example. Simply build NVIDIA's PyTorch conversion workflow. So I'm using the conversion skills, and blah blah blah, and then he start doing his work. So I'll come back to this and see later on, and then we examine the work he have done, and then it will run, just run the code and separately from the agent to just see how that goes. So so while he's doing this, will take a few minutes, but while he's doing so, let's just go back here and see what kind of a thing we built. So let me go back to slides. So essentially, when we're developing agent skills, essentially we develop three things, and the first two essentially we publish. The last one is kind of it's not a high quality, so we keep it we keep it local. We didn't publish. So essentially, the first part is so when we're developing skills, and the first part is you make sure the skills has a good authoring checks. Essentially, skills need to go through a lot of linked checks. Essentially, they're whether things drift, it has the right write the scripts, write the documentation, write references, and they're do you have an evaluation right, and do I have a right formatters, the size, and because if it is a size too long, and then you're overloading the agent token size usage, and they'll get confused. Do you have the right triggers? When certain words and say, hey, I'm going to convert, do this to federal learning project, does that trigger any actions? So there's the right triggers. Do the triggers are overlapping or not? They're confusing or not? So there's a bunch of things you need, and also a lot of security related stuff and policies. So this is the first things you need to do that. The second part is the runtime. So essentially, how do I know this code? Even though I said it's a PyTorch, I could say I gave the same instruction per lightning and it's simply run. But how do the agent skill to detect, oh, this code is actually PyTorch, and I'm using PyTorch conversions, or this is actually Hugging Face, and how does it know? So essentially, we built agent CLIs to do statistics analysis, do the first pass. And so essentially give you a sense of based on the basic, and then go to the next one. So that way reduce the agent to random poking around, looking at the source code, and so get it more efficient to do that. And then eventually come to the agent. So this is kind of the second part. The last part is essentially the kind of the harness to evaluating. So how do you do? So far we have done is this kind of skills, and there's some skills used by other skills. Like for example, the external facing skills we have is convert to PyTorch, convert to Lightning, converting Hugging Face, convert to fast stats, right? So these are the ones. We also have some implicit, like a diagnose jobs or the ORENT. ORENT essentially say, well, I did an initial checking and still couldn't determine is a PyTorch or something, and then I'll run to do the additional based on the ambiguity of the request, and then I'll try to decide what to do. So that sort of things. And then there's other skills, Holger will talk about in the related to auto research. So then you say, well, okay, you build the skills. How do I know that skill even good? So that's where the harness we do. So essentially, what we did is using this harness to build two versions of a FLARE, and one with skills, one with the other, one essentially install the skills, the other one doesn't install the skills. And with the same job folder, same CLI, so make sure that it's exactly the same. And then build two Docker containers. And in this Docker container, and then we do a kind of essentially a paired round, and then try to see what to give all the agent trails in terms of events and all the other things, and to understand what is going on. So this is kind of just I just randomly pick one of the round I did yesterday. So in this case, it's a Hugging Face and skills and conversion case. So I'm using cloud node codec, and it was the models, and it's running on Ubuntu, and then which is running fed average for 3 rounds. And so in this cases, with skills, and I'm a little faster, but most important, I'm using much less token, and agent using less commands to query around, and structure scores in a certain structure I want to a certain way, so don't look in too much of it. And there are certain code quality I'm looking for, and but the other part is the accuracy metrics in these cases with skills is slightly better. So that's kind of things I'm looking for. But in many cases, other cases is even though you say, hey, this looks good, but if you look at the report sometimes has like a retry, recovery, agent failed and recovered. You're looking for those and see why he doing that. So it means that a skill have a not so clear instructions. So that's kind of things we're doing. Let me, before I jump to this, and I go back to seeing what he have done. So he's still building the things. Let me see. Okay, give him maybe another minute or so. Let's go back to this. So that's pretty much the main talk I was doing. I'm gonna, before I passing to Holger, and then I'll actually come back to the exam demo in this, and then I give to Holger. So we have an event coming in this September. So this is our annual event called NVIDIA FLARE Day. So it's 15, 16, and 23. So the 15 is our workshops, and we're going to dive deeper into our latest stuff, and it's something we haven't get a chance to talk here. In the next September, we're going to talk more on that. And then the 16 is a US and European, time zone events. We have a lot of stuff I mentioned, like Eli Lilly, Cancer AI Alliance, and Rhino, Duality, Affairs and Drug Discoveries, and JP Morgan, UK Bristol, Flip projects, and Oak Ridge National Lab, and there's many more. Deloitte, a lot of talks on the real world use cases. And last year we had about 44 countries and about a little over 300 institution participates. So we expect that there's a lot more in this year. Also on the 23 is the APAC time zone, essentially California evening time. And that's mostly geared for Asia, like Singapore, India, China, Taiwan, and we have a lot of several talks from Taiwan, Singapore, and the UAE as well. So stay tuned on that one. So don't miss it. It's free and it's online. So you register on the link. Okay, let me go back one more. So let me. He wanted to do that. He basically finished it and he might try to run it. So let me go to this code and let's see what he's generating. You notice here I got these red of code. So first one, he's trying to prepare the data. So essentially he to go to split the data, because I'm telling him to have more than one guy split the data. So he have this little code to do this. But the important part is remember I have this client.py, essentially our client API, as told you, 3-4 lines of code. So he created this piece of code and try to do the client API. See this? Import, client as FLARE. And then if I go to the main code he said, hey, FLARE init, and then the rest of the code is the same as before. And then he add in this while FLARE is running. You see this? And then he say, oh, I want to receive a model. So FLARE receive. And then he load this model into the current model. So model.loads this. And then it do, if you require evaluating, if it is evaluating test, he simply return. But it is a training and evaluation, he just continue. And eventually he send this model, FLARE send model back. So essentially this is our client code. And then he create this another job.py. Essentially this is our recipe API. So the recipe.execute, and there's a environment. So the build a recipe. So where's the build a recipe? Somewhere here. See the build recipe using fed average. So he did that. Okay, so let's just, while he's running, I'm going to run in here directly. So I already in this PyTorch version. So if I look at this code, see currently have the source now have this job.py, client.py on that code. So what I'm going to do is I'm going to do Python job.py, see how that goes. So he starts running. Round 0, I just asked him two rounds, and he finished. So this is kind of it gave you the these these are validation scores, blah 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 and all that stuff. So the agent is still doing it because he finished the run and he also compiled the style check, the code and all that stuff. So he was doing all that stuff before. So actually, he did it. He finished. So he also run it. And then he said, okay, I have run 2, accuracy is this, loss is this, and then here's artifact. And so this shows that literally, without you doing much, you give a little prompt, agent, I'll just do this for you. So the same thing for Fed average and all the other frameworks. With that, I'm going to pass to Holger. Or you have a question first before I already took too much time, I guess. All right, so maybe you can ask question later, since I probably took too much time. So you can ask question on the chat and we'll try to answer later. Holger.
Hi, you can see my screen, right? Thank you, Chester.
Yes.
Okay, so one of the new skills we're also developing is around AutoFL research. Trying to automate some of these federated learning experimentations that you need to do in federated settings. So let me talk about that. One reason that federated learning is kind of challenging to adapt to new tasks is that you have now a distributed systems with many hyperparameters, right? And every time you want to apply this to a new data set with a new metric, you have many decision choices to make, like what federated algorithm do you want to try, what hyperparameters for your model architecture, learning rates, training workflows, aggregation methods do you want to use in order to optimize your training algorithm on that task. So all these choices require typically a lot of manual iteration, literature review for researchers, which we hope that agents can be very useful in helping streamlining. So AutoFL is using the latest AI agents to automate some of these procedures. And this fits pretty nicely into some of the history of auto machine learning and auto federated learning works from recent years. We actually worked on this topic for many years. In 2021, we had auto fed average, which tried to do a data-driven approach to learn the aggregation weights for federated averaging. We did federated neural architecture search to find like the best model architectures. Using also around the same time, we used reinforcement learning to do more of the hyperparameter optimization of all the different hyperparameters you can tune in a federated systems, server-side learning rates, client-side learning rates, batch sizes, and so on. But now with the coding agents, you really can expand kind of the search space of what is possible to explore, right? Rather than just tweaking hyperparameters in your training algorithm or the model architecture, the agents now can actually also search the literature for relevant techniques and algorithms. They can even propose ideas to explore and then implement code to try out new algorithms within a constrained harness, right? So that the experimentation stays valid. So we are now we are really expanding the auto federated learning, which was basically a federated hyperparameter optimization, to the next level, which is the agentic AutoFL research. And this work really builds on some recent advances in the field. I would say the Karpathy's work on auto research was a strong inspiration for this as well. That showed like agents doing research workflows autonomously for many hours, days. People have been working on doing rich literature review proposals that we also integrated, like the Camila project. And then, of course, we build on top of NVFLARE as the execution substrate, right? That makes sure that everything the agent is building is still valid within the federated learning execution environment, and it can utilize the existing library, utilize the existing recipes and APIs to the most efficient use. So if you think about this in one picture, you basically, as a human user, you would be defining the main goal, your data set, your task. You can specify some compute budget constraints and maybe give some initial guidance via a prompt. But then we basically use the auto-run feature or autonomous features of the agents to let the agents explore new recipes and parameters, compare the results, do literature reviews when necessary, and therefore explore the best FL solutions. And then NVFLARE is running the experiments and doing the evaluation and keeping everything transparently reported in a ledger that can be analyzed later on for record keeping. So the important thing here is that we have to define a set of skills. Again, building on what Chester explained earlier, we build basically a skill harness around this AutoFL research that makes sure that the agent doesn't find shortcuts to kind of optimize the metric in a way that defeats the purpose, right? I think one of the experimentations was that without our skill harness, the agent would, for example, just switch from federated learning to centralized learning to optimize the metric and get a better score within the same compute budget. And that, of course, kind of defeats the purpose. So the skills add a lot of additional tooling and constraints around the agent to make sure that it's not bypassing the experimental setting, and we actually make sure that we're comparing results that show that the training gets better rather than just the agent is tweaking what is being measured and therefore gets a better score. So the typical workflow is like this. We have the agent proposing a candidate. It might be running a validation step, a small smoke test to make sure that everything is running. Then FLARE runs the experiment, logs the result and metrics and training artifacts, and agent is reviewing, then potentially refining the candidate, maybe tweaking the parameters or discarding it if it's not successful. And then we have this literature review watchdog that if the score is not increasing after a certain number of candidates, it would detect a new round of literature review to basically try new ideas, new relevant papers to try out algorithms like, dealing with data heterogeneity, try label smoothing, try a new federated learning aggregation algorithm to deal with this particular data set and task. And yeah, in practice, you can see this working quite well. So this is like a CIFAR 10 example with 8 simulated clients on a heterogeneous data split. And starting from a baseline implementation of Fed averaging, the agent explores different candidates, finds new algorithms, and then you can see here, after it's getting stalled for a while, the purple line indicates a literature review being triggered. And often we don't see like a significant jump in the performance after the literature review, just because it found some new idea to try. And yeah, after running this overnight, you can give it a certain number of candidates to try, or just leave it run unlimited. You will see an improvement in most cases. So if you're interested, we have much more details in our archive paper that was published quite recently. And I will also show a few more results here on the Flumpy healthcare datasets. These are pre-partitioned healthcare benchmarks for federated learning, mostly around medical imaging, but also some healthcare like ECG data sets, so like healthcare electronic signals. We achieve a clear improvement of the baseline implementations that are provided, and sometimes even outperform the state-of-the-art performance. There's also a caveat that was shown in this benchmark is that, you know, for this TCGA dataset, the agent did significantly improve over the baseline for a particular seed, but then when you repeat the same training pipeline with different seeds, then that was not a robust improvement. So that shows you that, you know, if you have enough compute resources, you might want to run this even with multiple seeds at the same time to compare. So that kind of trade-off with, you know, if compute resources versus the number of candidates you can try, that is something you need to be aware of. We also tried it on the LEAF benchmark, which is a more diverse tasks across different modalities, different like computer vision and language tasks. And in all of these, we get like a significant improvement. And we also compared here for a feminist. We compared with some of the classical hyperparameter optimization techniques and grid search, and then the full AutoFL you know, search space with some model architecture variants that the agent explored. We achieved the best performance gains. So now with the next release, the 2.9, this AutoFL skill is or this AutoFL research topic was packaged as a skill, so you can install it and then prompt your agent to use it on an existing job in FLARE. So this kind of builds very nicely on what Chester demoed, basically using agents to build your job.py, convert your existing training pipelines to NVFLARE, and then use the AutoFL skill to optimize it for a given task. And typically this is like a mock example, but you should be able to see the agent running in the background, optimizing the skill, optimizing the job and giving you some improvement over time. And how this works behind the scene is that the AutoFL skill will instruct the agent to inspect the job and actually prepare this AutoFL.yaml file, which then can also be inspected by the human and maybe adjusted as to what kind of parameters can be adjusted, and you can define additional constraints as to the mutation surface, so to speak, of what can be optimized. So we then have I would say, a much smaller skill on top of this. Like after you complete your search campaign, you can also use the AutoFL report skill to give you a summary of what worked, what didn't work, where's the literature, papers for the particular algorithms that were tried and implemented and so on. And this kind of convergence curve is implemented in this AutoFL reporting skill. So those two kind of go together. Okay, and then the skill is designed to work in in simulation environment, but then also can work with POC and production environment, right? So the agent is basically assumed to not change any of the underlying permissions assumptions in FLARE. So if you can have an agent submit jobs to the production system in the same way and look at the results and modify the job, submit a new job, and iterate in that way. So yeah, if please try it out. Everything is on the GitHub. You can check the archive paper for more details, and published skills packaged in the next upcoming release. And if you have any questions, please let me know.
Thank you, Holger. I think and since we're a little behind schedule, we're gonna switch directly to Peter. So if you have questions, directly post on the chat.
We can. I think I can go a bit quicker. So if there are particular questions for Holger right now, we can have a few while I bring up my slide.
I think somebody raised a hand. Yeah, if you just unmute yourself. Oh, if you don't want to ask, and directly put on the chat.
Can you all see my presentation?
Yes.
Yep.
Okay. So let's see. Chester mentioned earlier in his introduction about all the different use cases, and just as the overall, we have different clients, different hospitals in this example that participate. One of the challenges that we see is that the variety of hardware and deployment systems that people use in these federated systems is very diverse. On the one extreme, there's basically somebody has a single desktop server, somebody sitting on somebody's desk with one or a few GPUs in it. Then there's people using Kubernetes clusters. And on the other extreme, we have people running HPC clusters with 10,000 plus GPUs. So we want to make sure that FLARE works across all of these systems. So in this particular case, maybe we have a server running on, a Kubernetes cluster, and then we have clients that run, on Docker, on Kubernetes, or Slurm. So in the previous release, 2.8, we added very good native Docker and Kubernetes support. And in 2.9, we add Slurm, native Slurm support. And for people on the call who are not aware of Slurm, Slurm is the scheduler that's used on large-scale HPC clusters and a lot of large-scale GPU GPU training and machine learning training.
Yeah.
Talking, maybe you can go mute.
This is...
Or Chester, you can mute them. And also at universities and research institutions, Slurm is very popular for running GPU-based jobs. So our goal has been that we want to be able to run a FLARE job across this very wide range of deployment environments without actually changing the job. So the examples that both Chester and Holger gave earlier, we want this code to be run across all of these federated systems without actually having to change the job. So that's kind of what we achieve in 2.9. So first, a little bit of detail on, I'm not going to go too much in detail here, because if you're not that familiar with Slurm and how it operates, it might otherwise not be that relevant. But we allow FLARE to run on Slurm both for the server and the client, and we can run them on a gateway host, which is often also called a login host. It's basically something on the outside of Slurm that you can run permanent jobs on. So typically you would run the server and the client parent job there. And then as jobs get launched, they will be launched on the Slurm cluster. It's a detail in the feature, but if you run Slurm, you will realize that it's important. Slurm's clusters can be run in many different ways with many different types of containers. And so we support both what's often called bare, which means no container, and you just run it in process. We support Apptainer Singularity, and we support Pixis containers and root containers. So no matter which flavor of Slurm you use, we should support it, and if not, we would like feedback on it. And so you should be able to run on your Slurm cluster native FLARE, and we will auto-scale. One of the important parts of both the Slurm capabilities, Docker and Kubernetes, is that is the auto-scaling capabilities that these frameworks have. So if you need a certain amount of GPUs for your federated learning job, but you don't want to allocate that all the time, only when the job actually gets run will we allocate Kubernetes pods or Slurm allocations or Docker containers. So it's very we don't keep the GPUs for all the time. We only keep them during the job. So if you occasionally run federated learning jobs, running them on these kind of systems is very convenient. And now the question now is obviously, okay, how I need to specify my job, and I need to specify a particular amount of memory or GPUs or CPUs. How do I do that? So when you launch a job, you have this resource spec that you can give to the job. And you can specify, number of GPUs, CPUs, and memory that the clients will need. And then FLARE will automatically, dependent on which infrastructure you use, translate that in the correct options. So if you run this on Slurm, it will use the correct Slurm parameters when it launches the job so that you actually get the CPUs and memory and so on that you asked for. But if another site uses Docker, we will then use the Docker command line to correctly get the quotas and limits so that you get the right amount of memory, and then you don't go over it, so that different jobs don't compete with each other. Same with Kubernetes. So on the server side or as a user, you just say how much memory you need, and then you don't even need to be aware of what a particular hospital or client, what they have as infrastructure. If they use Kubernetes, Docker, or Slurm, it will just work. We also support, I don't mention that in these examples, we also support not using containers, so just native in a process on a site, but then we are not able to constrain the usage of the memory and GPUs accordingly, because we don't have that capability then. So it is so FLARE also runs just normal without any of these infrastructures, just on a server. But then of course you won't have these capability. But this is very convenient because it removes the, you set up a site one way, you configure it with all the right parameters for your, Docker, Kubernetes, or Slurm, but then the users don't have to be aware of it at all. Of course, this is kind of the same thing. It translates these things to the appropriate fields for each of the environment. Of course, if you want, you can still override it. So you could still say, in Slurm, you can give it particular Slurm parameters or particular Docker parameters or particular Kubernetes parameters. So the flexibility is there, but it's set up so that you don't have to do it. But you could, in your job, use particular configurations for each of these environments. The other main advantage of using both Docker, Kubernetes, and Slurm is that because they enable very good sandboxing with the containers, is that from a security point of view, each of these jobs is totally isolated from the others. So not only can they not use other jobs' resources, GPUs and memory and so on, but they also are very well contained from a security point of view. So you can very narrowly control which data they have access to, or which secrets they have access to, which databases they can access. So that's can all be set up that way. So in short, we support, I think now with 2.9, the major deployment mechanisms that are out there, from a single server using Docker to Kubernetes clusters to large HPC clusters. Users shouldn't be aware of any of that. So if you run a federation across these heterogeneous systems, it would work. And obviously, these systems can run both on-prem and in the cloud. You can run, the Kubernetes clusters in the cloud or on locally, or same with Slurm. However you run it, it should work. And if it doesn't, we'll send us feedback and we'll look at it. And from a user perspective, it is all transparent. You don't have to be aware of it. You don't have to understand Slurm or at all to use Flare. We will translate it and manage it for you. So one job and a portable contract that then runs across all backends. And yes, and we have more, as I said, we can run just not using containers, but then some of these constraints can be implemented. Okay, so we have in the documentation lots of examples and how to use it. And coming out in 2.9, which is soon there, but everything is already in GitHub. So if somebody wants to have a look at it earlier, you can. That's it for me. And now we have, 5 minutes for questions.
Yes, any questions? So you can see that Flare has been developing, from skills to skills. So skill in the different kind of a deployment environment, Kubernetes, Slurms, Dockers, and agentic skills. And we're developing, skills for agents. And we're having more, about this. So for today, so anybody has a questions, since we don't have a lot of people, 30 or so, if you have a question, you can unmute yourself, directly ask, or you prefer to, you can put on chat. Okay, if not, so I guess we'll see you in Q4 webinar. So that probably close to the end of the year. So hopefully we'll see you soon. Thank you very much for your attending. Okay, bye-bye.
Thank you. Bye.
Thank you. Bye.